Hi everyone, let's continue with lesson 23 and do some examples of normal approximations to binomial distributions. Example 1 is our classic coin example. We will flip a fair coin 100 times. Let x equal the number of heads in the 100 flips, so a head is a success. Approximate the probability that we win our bet. Now our bet is that the coin will come up heads between 45 times and 55 times, inclusive. So we win the bet if the coin comes up heads exactly 45 times, or exactly 55 times, or anything in between. These bars do matter at this point. Describe the distribution of x. Well, what kind of distribution is it? It's going to be a binomial distribution where n equals 100 trials corresponding to the 100 flips, and p equals 1/2 because we're flipping a fair coin. We're flipping a fair coin, so p is 1/2. This is a discrete distribution, so the bars matter at this stage. In part B, we're going to verify that a normal approximation to this distribution would be appropriate. So we need to verify that NP and NQ will both be at least 5. And by the way, the 5 here does not come from algebra. It comes from practical observation. It's like the n greater than 30 condition from the CLT. Okay, well, NP, n is 100, p is 1/2, n times p is 50, which is way over 5. NQ is 100 times, again, 1/2, because if q is 1/2, if p is 1/2, then q is 1 minus p, or 1 minus 1/2, also 1/2. 100 times 1/2, again, is 50, which is way over 5. If both NP and NQ are way over 5, then we expect the normal approximation to do a very good job, especially with continuity corrections. So our mean here, by the way, is given by NP, which is the same formula as this over here. So when you calculate NP, you're also calculating the formula for the mean, or the expected value of x. It's 50. N times p is 50, which is the expected number of successes, or heads. This makes sense because if you're flipping a fair coin 100 times, then the expected number of heads, it makes sense that it's 50. By the way, NQ is also 50. That's the expected number of failures, or tails. These are both at least 50. In fact, they're way over 50. So the normal approximation is applicable in this case. C, describe the normal distribution that can be used to approximate the distribution of x. So what is the distribution that we can apply? Well, as I just mentioned, the mean is NP, or 50. Okay, that's the first key parameter for the normal. The mean mu is NP. We work that out. 100 times 1/2 is 50. Technically 50 heads, if you want the unit. The standard deviation, sigma, is given by the formula, the square root of NPQ, which is the square root of 100 times p is 1/2, and q is also 1/2. It turns out to be a nice integer, 5 heads. Standard deviation. Which means, by the way, by the 2SD rule, that we would really expect, with about 95% confidence, that we'll get between 40 and 60 heads if you use the 2SD rule. But what about 45 to 55? So we have our parameters here. So therefore, we're saying that x, the number of heads, has a distribution that is approximately normal, with mean 50 and standard deviation 5. All right, now let's apply continuity corrections and rewrite this probability expression in terms of corrected x. So we're going to nudge or move these boundary values slightly and take z-scores later on for those new boundary values. But I need to move these slightly in order to apply the continuity corrections. Well, what are the real numbers that round off to 45? And what are the real numbers that round off to 55? The picture looks like this. The real numbers that round off to 45 are the ones between 44.5 and 45.5, as we said in the previous video. The real numbers that round off to 55 are between 54.5 and 55.5. So this block represents the integer 45 from the binomial. This block represents the integer 55 from the binomial. But remember, we win if we get exactly 45 heads, so we do include this block. And we also win if we get exactly 55 heads, so we pick up this block. And we win for anything in between, 46, 47, and so forth. So we want to shade in this entire region here. So ultimately, what are our outer goalposts? Our goalposts are going to be from 44.5 out here to 55.5 out here. These are the true boundary values that'll trap all of the shaded region inside of here. I'll put this in red for emphasis. Again, we want 44.5. We want 44.5 as our left key goalpost and 55.5 as our rightmost key goalpost. And we ultimately want z-scores for these new boundary values over here. These are corrected values for x. This is to take care of the awkwardness of having a continuous normal distribution approximating a discrete binomial distribution. In part E, find the z-scores for the boundary values for these new corrected values. What are the z-scores for these? 44.5 and 55.5, which traps all the stuff in the middle that I want. And by the way, at this point, the bars no longer matter. So if you want, you could put bars over here, but since we're dealing with a continuous normal distribution, it doesn't matter at this point whether you put bars or not. All right, find the z-scores for these boundary values. Well, for 44.5, the z-score is x, which is 44.5, minus the mean, which is 50 heads, remember, all divided by sigma, which is 5 heads. Remember, it's basically heads divided by heads, right? Heads minus heads is heads. Heads divided by heads, no unit. Z-scores have no units. So z equals, all in heads, 44.5 minus 50, the mean, all divided by the standard dev, 5. Don't forget to process the numerator before dividing. The result is negative 1.10. And why does it make sense that the z-score is negative? Because 44.5, the boundary value we're looking at, is less than the mean of 50. So the z-score is negative. That's a good check. What about 55.5? Well, since these are both symmetric about 50 heads, the mean, you could just use symmetry and say it's positive 1.10, or you can go through the formula again, where you replace 44.5 with 55.5. This time you get a z-score of positive 1.10. So these are the z-scores that correspond to the corresponding corrected x-scores over here, the boundary scores. In part F, write the corresponding probability expression for z. So write this here, this expression in terms of corrected x, in terms of z. Well, instead of 44.5, we have a z-score of negative 1.10. That's the z-score for 44.5 heads. Instead of 55.5 heads, we'll convert it to its z-score, 1.10, positive 1.10. So now we're focused on this probability over here, and we can use the software or tables for z-scores for a standard normal. Now, in the stated problem, I give hints. We're going to approximate the probability of me winning the bet using these hints for the z distribution, the standard normal. We're going to use the probability that the area or probability to the left of positive 1.10 is 0.8643, this big chunk over here. Of course, it's way bigger than 0.5. And then I want this area or probability to the left of negative 1.10, which is smaller. is 0.1357. In fact, by symmetry, you can see that this and this are complements. These add up to 1. Again, that's by symmetry. If this were, for example, 2 or 3, then this symmetry idea wouldn't work. We wouldn't have symmetry. But here we do have symmetry. All right, so I have this big area. I have this small area. This looks like an in-between area or probability. So what do I do with these probabilities? I subtract them. Because what I want is this blue shaded area in the middle. In order to get that, I want the probability or area to the left of positive 1.10. I want the probability or area to the left of negative 1.10. These areas I got from the hints, right? These are the numbers I got from the hints up here, 0.8643 and 0.1357. What do? I subtract them in order, larger minus smaller. It better be larger minus smaller because the result cannot be negative. 0.8643 minus 0.1357 is 0.7286. So according to this method, we have about a 72.86% chance of winning my bet that the number of heads will be between 45 and 55 heads inclusive. Now, software can confirm this for us because software, like Excel, say, can apply this binomial probability formula. I hope this looks familiar from lesson 17 or 18. I think it was lesson 18, actually. Lesson 18. The binomial probability formula, which was optional. You didn't have to memorize it. But this was the probability of getting X successes out of N trials. And you didn't have to memorize that. This was the formula. Well, Excel can apply this formula. So what can Excel do? Excel can work out the probability of getting 45 heads using this formula, the probability of 46 heads, and so on, up to and including the probability of 55 heads. And in fact, I had Excel do that. According to Excel, if you flip a fair coin 100 times, you count the number of heads as successes, you let X be the number of heads, X will have a binomial distribution with N equals 100 trials or flips. We assume a fair coin. P, the probability of heads, is 1/2. And here we have the probability distribution table. You can see the probability of 0 heads is close to 0. This is using scientific notation. This is about 8 times 10 to the negative 31st. It's basically 0, just a little bit above 0. In fact, it's very close to 0 for these values of X. But then we start to register really, especially in the 30s or so, numbers of heads. And this is what we want. Here's P of 45, which we include. It's about 5%. Here's P of 55, which we include. It's about 5%. Notice that even the most likely number of heads, 50 heads, is not even 8%. Remember that total probability is 1, and it's being split up among all these different possibilities. And even the probability of 50 heads, the most likely number of heads, is not even 8%. You would not want to bet the farm or your house on a particular value of X, although P of 50 is the highest. So what happens when you add up all these probabilities? I had Excel do that by using the sum operator. It turns out to be this. To 8 sig figs, or decimal places, 0.72874698. Okay, which was basically what I gave you over here. The actual probability to 6 decimal places is 0.728747, which is basically what Excel is saying, 0.728747 to 6 decimal places. This is essentially exact since we're using the binomial formula. It's the correct probability to 6 decimal places. And it's pretty darn accurate. So our answer of 0.7286 was pretty good. That was the answer that we got, even to 4 decimal places. It was 0.7286, and that was pretty good. To 4 decimal places, the quote-unquote exact answer is 0.7287, up to rounding error. So the error here is due to rounding error. 0.7286, what we got from our normal approximation with continuity corrections, Very good. Now, if we had not applied the continuity corrections, we would have been pretty close, 0.6826. That sounds a bit familiar because we were talking about within about one standard deviation of the mean. So it's not so surprising that this is about 68%. But you can see that the 0.7286 is a fair bit more accurate. Although later on in the course, we're not going to bother with continuity corrections, and we may have to be satisfied with something like that. Actually, the 0.7286 is for 1.10 standard deviations. 0.6826, hey, if you had not applied continuity corrections, if you had taken z-scores for 45 and 55, you would have gotten z-scores of -1 and +1, and actually, this is the probability of being within one standard deviation of the mean. So yeah, we would have gotten z-scores of 1 and -1 had we not applied continuity corrections. This is what we would have gotten. Actually, the better z-scores would have been 1.10 and -1.10. So this was actually a bit more accurate. We get a bit more probability. Because remember, if we had just used 45 and 55, we'd be losing these pieces that are getting cut off if we had not used the continuity corrections. All right. Now, what about other wordings? What if we wanted the probability, in example 2, what if we wanted the probability of at most 45 heads? Does at most 45 include 45? Yes, it does. It includes 45 heads. And do we go left or right? Do we want lesser values or greater values? We want lesser values. So we want 45 and we want lesser values. Remember, what are the real numbers that correspond to 45 for the normal approximation? Between 44.5 and 45.5. Do we want 45 heads? Yes, we do. So we do shade this piece and also everything to the left. We want all lesser pieces as well, which means the true goalpost we want is at 45.5. The goalpost I want, there's only one because there's only one boundary value. I want the goalpost at 45.5, not 44.5, because I want all the shading to the left of this goalpost. So the probability that x is at most 45 heads is about the probability that corrected x is less than 45.5 heads. Again, I don't care if you put the bar here or not at the normal stage. At the normal stage, I don't care. What about part B, the probability of getting more than 55 heads? Does more than 55 include 55? No, it does not. More than 55 heads excludes 55 heads. And which way do we go? Left or right? Lesser values or greater values? We want greater values. But we do not include the 55 itself. We do not want the 55 itself. Now, the real numbers that round up to 55, what are they? The real numbers between 54.5 and 55.5. But wait a minute. Do I win if the coin comes up heads exactly 55 times? The answer is no. I don't want this block from 54.5 to 55.5, but I want to shade everything to the right of that block. So what's the true goalpost or boundary value I want for corrected x? In purple, I want this guy, 55.5. The probability that x is greater than 55 heads or more than 55 heads, it's about the probability that corrected x is greater than or more than 55.5 heads. Because this here is a true goalpost, 55.5, not 54.5. Again, there's only one boundary value. You only have to find one z-score, and you want a right tail probability. Some final comments at the end.